Class, welcome to the first Toolbox. The goal of these toolboxes is to introduce mathematical approaches to you before class so that we can spend our in-class time working together to apply these tools to the types of problems you might find in the environmental or earth sciences. Our first toolbox focuses on an introduction to vectors. Okay, so let's start by talking about what a vector actually is. A vector is nothing more than a sequence of real numbers. A vector might contain two numbers, it might contain three numbers as in the example above, or it could contain hundreds, thousands, or even millions of numbers. You can think of a vector as a table with only one dimension, but it is a useful tool for us to organize our data and to manipulate that data. We refer to the numbers or elements within a vector as its components. You'll also often hear different vectors referred to as n-vectors, where n is the number of elements or components in the vector. For instance, the vector v in this slide is a 3-vector. Vectors are very powerful and flexible tools. For example, the vector on this slide with 3 elements could be used to keep track of the heights of 3 different people. It could also be used to keep track of the temperatures at 3 different locations that you know are nesting sites for brown pelicans. Or it could be used to keep track of the distance that the undersea submersible Alvin has traveled during one of its dives. Basically, you can put any numbers that you want inside of a vector to keep track of them. These vectors are thus very flexible tools. Okay, so why is it that we want to use this mathematical formalism of a vector instead of just calling it a list of numbers? Basically, the answer is because mathematicians have developed a lot of tools for conducting different types of computations on vectors that allow us to undertake powerful manipulations of our data using the language of vectors. One of the most basic types of operations is scalar addition. For those who may have forgotten, mathematicians use the term scalar for any real number or any quantity that can be measured using a single real number. So basically, a scalar is just a number, like the number 3, or the number negative 2033.5, or the number pi. When adding any one of these scalars to a vector, we simply add the scalar number, for instance 3, to each of the elements in the vector. Okay, now let's talk about a concrete example. Our first example of a vector was a vector recording the height of 3 different people. Now, if those 3 people all step onto a bench that is half a meter tall, we can calculate their apparent heights by adding the scalar 0.5 to the vector v. Let's now call this new vector of their apparent heights h. H will be equal to the vector v plus the scalar 0.5. Since with scalar addition, we compute the new vector h by adding 0.5 to each of the elements in v, we can see that the new vector h will be equal to 2.4, which is 1.9 plus 0.5, then 2.1, which is 1.6 plus 0.5, then 2.2, which is 1.7 plus 0.5. We can also use scalar multiplication to multiply all of the elements in a vector by a constant number. For instance, with our original vector v with 3 elements a1, a2, and a3, we can create a new vector by multiplying each element by the scalar value c, and we get the new vector is c times a1, c times a2, and c times a3. Here's an example for scalar multiplication. I often work with crustaceans, such as krill, in the ocean. For crustaceans, we know that their dry weight, which is their weight once you dry them out and remove all their water, contains about 40% organic carbon, about 5% nitrogen, and about 0.1% phosphorus. So we could encode that information in the vector v. Now if I went out and collected a sample, dried it out, weighed it out on a balance, and found that it weighed 500 milligrams, I could use scalar multiplication to calculate the masses of carbon, nitrogen, and phosphorus in my sample. Let's call the new vector m. It will be equal to 500 times v. We then compute that m is equal to 500 times 0.4, and 500 times 0.05, and 500 times 0.001. M is thus equal to 200, 25, 0.5, and we know that our sample has 200 milligrams of carbon, 25 milligrams of nitrogen, and half a milligram of phosphorus. We can also combine scalar multiplication and addition. Let's go back to our example of measuring the temperatures at 3 different nesting sites for brown pelicans. We all work in the metric system, of course. But let's imagine that your friend went out to collect measurements for you one week and only had a thermometer that read in Fahrenheit. Well, we know that we can convert from Fahrenheit to Celsius by multiplying by 5/9 and subtracting off 18. So we can now write an equation that our new Celsius vector is equal to 5/9 times the Fahrenheit vector minus 18. We then compute it by multiplying each element by 5/9 and subtracting 18 from each element. We then find that the temperatures at our 3 nesting sites were 10.9 degrees Celsius, negative 1.3 degrees Celsius, and 21.4 degrees Celsius. At this point you might be asking yourself, why do I need to write this as a vector when I could just calculate this separately for each location? The answer is that eventually you may get to larger and larger vectors. Like, let's say you were actually monitoring 100 different nesting sites and took measurements every day for a year. You might stack them all into a vector with 36,500 elements. Or you might put them into a matrix, which we'll learn about in the next toolbox, that is 100 by 365. In either case, you have a huge number of elements and you don't want to compute something each time. But computers are really good at matrix and vector algebra. So learning how to use vectors and matrices will give you the necessary language that you'll need to tell computers to do all the work for you. So far we've discussed adding a scalar to a vector or multiplying a vector by a scalar. However, we can also add 2 vectors to each other. For instance, if we have the vectors v and u, where v has elements a1, a2, and a3, and u has elements b1, b2, and b3, then the sum of those vectors will be a1 plus b1, a2 plus b2, a3 plus b3. So why might we want to add 2 vectors? Well, let's go back to our example in which the vector v was the distance traveled in 3 dimensions by the Alvin submersible. If the vector v was the dimension traveled during the first hour of your dive, and the vector u was the distance that you traveled during the second hour of your dive, we can add the 2 vectors together to find the total distance that we've traveled. Adding vector v and vector u together involved adding each of the individual elements. So v plus u is equal to 10 plus negative 5, 28 plus 10, and 21 plus negative 12, which is equal to 5, 38, 9. The diagram shows you schematically how we add the 2 vectors together. The black vector is our original vector v, the green vector is our new vector u, or the distance that we traveled during the second hour. The red arrow shows the sum of the 2 vectors, which is the total distance that you've traveled over the 2 hours. We previously talked about multiplying a scalar by a vector, which creates a new vector. We can also use a dot product to multiply 2 vectors by each other, resulting in a scalar value. The dot products of 2 vectors is the sum of each element of one vector multiplied by the corresponding element of the second vector. In other words, you take the first element of vector 1 and multiply it by the first element of vector 2, then you add the second element of vector 1 times the second element of vector 2, then you add the third element of vector 1 times the third element of vector 2, and on depending on how many elements you have in your vectors. Like with vector addition, the dot product only works when both vectors have the same length. For instance, if we have vector v with elements a1, a2, and a3, and we have vector u with elements b1, b2, and b3, the dot product of v times u will be equal to a1 times b1 plus a2 times b2 plus a3 times b3. Okay, Now for an example of how I might use a dot product in my research. I sometimes study larval tuna and other fish in the Gulf of Mexico. If we tow a net through the water, we might catch a lot of several different types of larval tuna, because there are many different fish species that spawn on the clear waters of the central Gulf of Mexico. Often what I'm interested in is not actually the numbers of fish, but the biomass of the fish, which depends not only on how many fish there are, but also on how much each type of fish weighs. Let's say that we caught 651 bluefin tuna larvae, 1,908 skipjack tuna larvae, and 2,058 mahi-mahi larvae. If we wanted to compute the total biomass of all three fish species, we could calculate the dot product of these abundances and the average mass of each type of fish, which I've put into the vector u. The average mass of a bluefin larvae is 1.25 milligrams, the average mass of a skipjack tuna larvae is 0.98 milligrams, and the average mass of a mahi-mahi larvae is 0.73 milligrams. We can then calculate the dot product of v times u. It will be equal to the number of bluefin tuna, 651, times the average mass of bluefin, 1.25 milligrams, plus the number of skipjack tuna, 1,908, times the average mass of skipjack tuna, 0.98 milligrams, plus the number of mahi larvae, 2,058, times the average mass of mahi, 0.73 milligrams. If we plug this into a calculator, it's equal to 813.75 plus 1869.84 plus 1502.34, which is equal to 4,185.93 milligrams. We can also use the dot product to calculate the distance that something or someone has traveled. Let's go back to our example with the submarine. The vector v encodes the distance that the submarine has traveled in the x, y, and z directions. But of course it didn't go 10 meters east, then 28 meters north, then 21 meters up. It traveled in a straight line that took it a total of 10 meters east, 28 meters north, and 21 meters up. To calculate the total distance traveled, we can use a special property of vectors. The length of a vector is equal to the square root of the dot product of that vector multiplied by itself. So if we want to calculate the distance the submarine traveled, we first calculate the dot product of v times v. The dot product of v times v, of course, is simply the first element of v, which is 10, multiplied by itself, plus the second element of v, 28, multiplied by itself, plus the third element of v, 21, multiplied by itself. This works out to be 1,325. Now if we want to calculate the distance traveled, all we need to do is take the square root of the dot product. The square root of the dot product is the square root of 1,325, which is approximately 36.4 meters. So that's the distance that our submarine traveled. The last concept that we need to discuss is an orthogonal vector. Two vectors are referred to as orthogonal if their dot product is equal to 0. In 2 dimensions, vectors are orthogonal if they are perpendicular in the sense that you normally think of perpendicularity. Orthogonality extends the concept of perpendicular lines into multiple dimensions. Thus, for vectors with more than 2 elements, the easiest way to compute whether or not they are orthogonal is by computing their dot product and checking to see if it is equal to 0. We're going to come back to orthogonal vectors later in the course, but for a moment I want to just make sure that we are all on the same page about why we are discussing vectors. We saw a couple slides ago how we can use a dot product to compute the biomass of some fish. But of course we don't need a vector to do this. We could have multiplied the biomass of bluefin by the abundance of bluefin and added the biomass of skipjack times the abundance of skipjack and the biomass of mahi-mahi times the abundance of mahi-mahi. When we're only dealing with a couple vectors and each of those vectors only has a few elements, it is really pretty easy to answer the question without using vectors at all. But really what we're going to be doing in this course is learning mathematical language. Using these mathematical languages is really powerful because it allows us to talk to computers, and computers can do many computations for us very, very quickly. For instance, in that example with the larval fish, we had 3 fish and 2 vectors. In my actual research, I'll often do something like that with 40 species, and I might have not just a couple vectors, but instead 100 different vectors corresponding to different net tows that I've done in different regions of the Gulf of Mexico. In other projects, I've actually used vectors that had more than 1 million elements. In the age of big data, it is really important to learn the language of mathematics, because it will allow you to tell computers how to do the hard work for you. So keep that in mind for the next couple of weeks. We're going to start this course by learning the language of vectors and matrices, and we'll practice some of these basic concepts using some relatively simple problems that you can write out on a piece of paper. But the same techniques we are learning could be just as easily used with much larger data sets, like you might encounter in oceanography, meteorology, geology, or environmental science, or even in other fields such as finance, machine learning, or sociology.